Hello and welcome to this video. In this video we're going to go through the electric field strength and electric potentials. So we've seen in the previous video that we could say that the Coulomb force, so the force between two charged particles, is 1 over 4 pi epsilon naught q1 q2 over r squared. In order to define a field strength, there is also a second force equation that we can relate. In the same way that we have F equals ma, we have the electric field comparison of that, which is that F is actually equal to E times Q. Okay, so this is another formula that is on your formula sheet that talks you through the relationship between the electric field strength and the force. Okay, so just the same way as G is equal to ma, because the force acts on the mass, in electric fields it acts on charge, so the E is the electric field strength. And we said that we could define this electric field strength as just taking F and dividing by Q. So if I rearrange this, I get E is equal to F over Q, which means I can take this formula for F, and if I divide by Q, it doesn't matter which Q I divide by, but I end up with an expression for the field strength, the electric field strength, being E is equal to 1 over 4 pi epsilon naught Q over r squared. Okay, so I'm just getting rid of that second Q, and that means that in the same way that we looked at before, this field strength is a vector that is only dependent on this charge that is keeping it there. Which also means that if it's only dependent on the charge at the center of this field, it can be positive or negative. Okay, your field strength will have a different direction depending on what a positive test mass feels. Because if you remember, the definition of a field strength is that it is the force per unit charge felt by a positive test charge at a point in the field. Okay, now this is the definition of what we actually mean by the electric field strength. So it's the force per unit charge felt by a positive test charge at a point in the field. Now the force can either be a repulsive or attractive force, which means that the electric field strength would actually have to be positive or negative depending on if it's attractive or a repulsive force. So it can vary between being positive and negative. It is also worth mentioning that this only works for a radial field. Okay, we can't have this kind of expression for a uniform field because we see there's a slight difference. Okay, so this we're going to note as being the radial field. Okay, and we can know it's a radial field because of this r squared, because you have a radius dependency in the distance that you are away from the center of the field. You'll end up with just this is the field strength in a radial field. Now we're going to look at a whole separate set of videos on the uniform fields, because that actually has more practical applications rather than just theoretical applications like this. But we can see for these fields, we can also make the same assumptions that we did for gravitational fields in looking at the field lines. So the field lines, we said in the gravitational fields, actually represent the field strength. So the field lines, the more dense, or actually let's just say the field line's density is proportional to the field strength. Okay, now what I mean by the field line density is that if I have a field, and I'm just going to take a radial field for this set of videos, And if I have a group of field lines that look like this, I end up with a kind of average field line density. So the field strength is small. If I then was to say that the field lines actually looked like this instead, because I have many more field lines, it means that I have a much stronger field. So I'll have a much larger field strength from this. And from here, we can go forward and then look at the potentials in an electric field. So potentials we have defined before as being the work done per unit mass. Now we're obviously going to change that to charge. And we said there was a relationship between the field strength and the potential. And this is also true. We said that before, if we take a differential of the potential, so the derivative of V with respect to the distance is the electric field strength. So it means that essentially all we have to do is change that expression slightly. For those of you who can't do derivatives because you haven't taken maths, that's completely fine. You don't have to know how to do the derivatives. It's just a way of remembering it, but it's on your formula sheet anyway, so it doesn't really matter. So we can just say that from the formula sheet, the equation we have for potentials is that V is equal to 1 over 4 pi epsilon naught Q1 over R. Okay, so this is now not dependent on R squared anymore. This is dependent on R. So this is the formula for potential. Okay, and we defined it. So the definition is that we have the work done per unit charge to move a positive test charge from infinity to that point. Okay, and we say that each point in a field will have a value for potential, and if we wanted to then map out those potentials, we could do that by equipotential lines. Now it's also worth noting this is a scalar quantity. Potential doesn't have a direction. However, in the case of gravitational fields, we said they always have to be negative, because by definition they require energy to escape the field to get to zero energy, so they must start as being negative. In this case, we don't actually have that always being negative. It can be negative or positive depending on what the charge is. So even though it is scalar, it can be negative or positive depending on the charge. And if the charge at the center of this field is positive, then your potentials are positive. Okay, that's because if you were to have a positive test mass in the field, it wouldn't require you to put in energy to take it away, because the forces that are there will naturally push the positive test charge away from the center of that field. If you had a negative test charge in the field, then it would mean that it would be attracted, so you would have to put in energy to take it in the opposite direction, to move it away from this positive mass or positive charge. Okay, so the potentials can be negative or positive depending on the charge of the charge at the center of the field. We can still say we have equipotential lines, but these are slightly different. So we can have, for a single radial field, we'll have the same thing. So if this is, for example, a positive charge, let's say we had these kind of field lines with an average field line density, I'm not going to draw the arrows on these, but we should know they always go from positive to negative, so they all point outwards. If I go a certain radius away, since this potential equation is only dependent on the radius, going along these lines will not change the potential. Okay, anywhere, if I were to move in a circle along these lines at a constant radius, I wouldn't have to do any energy transfers. The only way to change potential is to move towards or away from the charge, and that is going to require some energy transfer, like we've said in gravitational fields. So we're going to do a separate video looking at how can we look at energy transfers in these cases. But if we also have something that has a positive charge and a negative charge, we will also see a similar sort of case. If we were to draw the field lines, they're going to be attracted to each other. So I'm going to get this kind of field where all of the lines are going to join because this is an attractive force. And I have a similar kind of group of equipotential lines for when I have two gravitational field masses being pulled together, because it's still an attractive force, so you have something very similar. And you end up with equipotential lines that look something like this. Okay. However, there is a difference then when I have two charges that repel each other, because I no longer have a constant line between these two. I now have to look at the field lines changing. So if I were to look at a positive charge here and a positive charge here, this would be the same if I did two negative charges. These are going to be perfectly normal and the same. So these kind of field lines pushing the other directions will be the same. But we said that these ones are going to curve so that they never actually meet. So we're going to get field lines that look something like this. Okay. Now, in order to get the equipotential lines, there should be an equipotential still exactly halfway between them. Okay, because at this point we should remember that potentials, because they're scalar, will just sum together. Okay, so this is a very important thing, and we'll do a practice question showing what happens when we just add together potentials after this video. It means that if I have a potential due to this charge, as long as these two charges are the same, I will get an equipotential line straight down the center. Now I'm going to get equipotential lines that are going to do this kind of thing, but they will be more skewed than they would if they were both attractive. But you still end up with similar shapes of equipotential lines. They're just slightly different based on the fact that you're now repelling rather than attracting. So in order to get the potentials to be the same, you then have to be different, varying distances away from each mass or each charge. Okay. Then the final thing that we need to also specify now is, what about a potential gradient? Okay, what if we want to then change potentials? How well could we do that? Okay, so if you remember a potential gradient for gravitational fields, we said it was the change in potential divided by the change in the distance, and we said we could draw a graph for this. So we could say that I'm going to assume, so before I draw a graph, because it's not going to be the same in all cases, I'm going to say specifically I have a positive mass, positive charge with a plus q at the center of this field, and I'm going to have a positive test mass at the edge here. So this is a positive test mass, which means my potential is going to be 1 over 4 pi epsilon naught q over r. So because this is a positive mass, my potential is positive everywhere. Okay, so I'm going to end up with a potential graph that is going to look something like this, where I have v on the y-axis and the distance on the x-axis. Now this is still a V is proportional to 1 over R, so this is still an inverse proportionality, so we're still going to see something that looks a little bit like this. And we said that if we take the gradient here, we're going to end up with the potential gradient. And how quickly this changes is actually a measure of the field strength. Okay, so this is another way that we can define the electric field strength based on how quickly does the potential change as we travel away from the charge at the center. If the charge at the center is very big, we're going to see that there's going to be a very drastic potential change as it goes away. But if the potential is if the charge at the center is really small, then we see a smaller change. So we end up with a very large field, very large electric field strength for very large charges, and a small electric field strength for smaller charges. And these graphs can then these graphs can then prove that we can have electric field strength as both being positive or negative, because if I change this situation and I instead had a negative charge at the center, then all my potentials become negative, and I will end up with a graph that looks like this, as we did in the gravitational fields. And so this means that if I take a gradient here, this is now my electric field strength. Now this gradient is negative, whereas this gradient is positive, so it does matter if your gradient is or if your center charge is positive or negative, because it's then going to affect the sign of your potentials, the sign of your electric field strength, the sign of the forces. Everything changes, so it does matter to know what the sign of the charge at the center is. So to summarize all of this, we can say that we have the electric field strength we could write as E is 1 over 4 pi epsilon naught Q 1 over R squared. For a radial field, we're saying that E is a vector, and we defined it as the force per unit charge, which means E has units of newtons per coulomb. And we can also say that the electric field strength could also be measured as delta V over delta R, where in this case still a vector, but now we could measure it in volts per meter, because we're saying the V is the potential measured in volts, and R is per meter, so distance between it. Then we can say that potentials, V is 1 over 4 pi epsilon naught Q over R. So potential are scalar, and they are measured in joules per coulomb. So this is work done per unit charge to move from infinity to that point, and the work done is a measure of joules, and the charge is a measure of coulombs, so our scalar potential are measured in joules per coulomb. I'll do an example question of what happens if I were to put now multiple charges in a system. How would that affect forces, and how would that affect the potential at an individual point in that field? Thank you for watching.